in my last lecture I discussed how to determine a generalized expression for voltage drop for a feeder which is connected to a substation, and the substation service area can be of different shape. It can be square, it can be hexagonal. Basically, these two different shapes of service area under a substation is discussed. Okay. And if you remember my last lecture, you have seen that this expression for voltage drop for primary feeders, it is mainly proportional to the effective length of the feeder, and this effective length of course depends upon how the load is connected, and also it depends upon the loading of the feeder. And apart from that, if you these are the two parameters, one is effective length, another is loading, on which voltage drop depends. And there is a proportionality constant, because voltage drop is ultimately proportional to the effective length and the loading of the feeder, and the proportionality constant we call it constant K. And in my last lecture I discussed that I will show you how to derive this constant K. Okay. So, in this particular lecture I will start how to derive the constant K. Now, look at this slide where we will be basically deriving this constant K. Okay. So, you know that we have this a primary for a primary feeder, the effective impedance Z, it depends upon how the loads are connected. This is not nature of the load, basically how the loads are connected. This nature of the load stands for how the loads are connected. So, it depends upon how the loads are connected, or load configuration you can say. Okay. Now, if we have a lumped load, the lumped load means all the loads are aggregated and it is connected at a particular point. Now, under this condition, this effective impedance is Z multiplied by L, where L is the length of the feeder, Z is basically impedance of the feeder per unit length, its unit is ohm per kilometer or ohm per mile, depending upon what type of unit you are using for representing the length, and L is basically length, effective length of the feeder, effective length of the feeder, length of the feeder. Now, this effective length is equal to the actual length when we have lump sum load connected. That means, loads are aggregated and connected at the end of a distribution line like this. This figure shows that this is the substation, and here we have all the loads connected, and this is the power demand of that particular load. Now, if the load is uniformly distributed, the effective length becomes, so L effective becomes half of this actual length. So, this is already derived, and if you put over this expression, then you will get the actual impedance is half of Z L. Similarly, when you have load with an increasing load density, it means that it is of a triangular service area. So, this is basically representing triangular service area for a feeder with uniform load density, with uniform load density. Okay. So, when we have that type of feeder, this effective impedance becomes 2/3 of actual impedance, that is it is basically because the effective length becomes 2/3 of actual length. So, here L is representing the length of the feeder as I explained, and this effective length is equal to actual length only when you have lump sum feeder. So, here L effective is basically L, but apart from that on all other cases L effective becomes different than L, and accordingly this impedance value will change. Now, what we will do in this particular section, we will try to determine the expression for this proportionality constant K, which relates that voltage drop with the effective length of the feeder and the loading of the feeder. Okay. So, in order to derive that, we consider here basically a distribution feeder with lumped load, distribution feeder with lump load. Okay. Here lump load means loads are concentrated at the end of this feeder. So, this is the end of the feeder, so where all loads are coming concentrated or aggregated, and this is what the load demand. It is represented by P r plus J Q r. Okay. And this impedance of this feeder is represented by R plus J x. Okay. And this V s basically this voltage at substation or voltage at sending end. So, this is basically voltage at substation, and this V r basically representing voltage at load end, voltage at load end. Okay. This I is basically representing load current or current drawn by this load current. Okay. So, I is basically representing load current or current drawn by the load. Now, this bar symbol, this bar shows they are phasor quantities. So, this symbol bar is showing that they are phasor quantity, phasor quantity. Okay. So, we have a load which is connected at the end of the feeder, and this L is basically, this is L is basically representing the length of the feeder. This is length of the feeder. So, we have a feeder whose length is L, and it is connected to an aggregated load or lumped load at the end of this feeder, which is shown over here. And due to that, I, this current I, that is load current, it remains constant throughout this line, and this V s is representing voltage at the substation or the source side voltage, and V r is basically representing that voltage at the load end or receiving end voltage, or you can call it as load end voltage. Okay. Now, what we will do first for this analysis, we will try to have a relationship with a sending end voltage and receiving end voltage. Now, how to get the relationship? We will simply apply Kirchhoff's voltage law here, KVL we will apply, and we will get a relationship of V s and V r. So, what will be the relationship of V s and V r? This V s would be equal to V r plus this drop across this feeder or voltage drop due to this line impedance. So, this drop will be equal to nothing but I multiplied by Z, and Z is of course R plus J x. Okay. So, this is what we get by applying KVL at this sending end and receiving end side path. So, if we apply KVL at this path, you will get that voltage at this point would be equal to voltage at this point plus voltage drop due to this impedance of the feeder, and that voltage drop is equal to I multiplied by R plus J x. Now, these are all this is a complex equation because these are phasor quantities. Okay. And with this equation we can draw the phasor diagram as well. We can draw the phasor diagram. How can we draw phasor diagram? here you look at. In order to draw the phasor diagram, we have to consider some phasor as a reference. So, here we consider receiving end side voltage or load end voltage as a reference. So, we put it over here, this is the reference. So, since we have considered this reference, so we can write that angle of that reference phasor is 0 degree. So, it is represented here at an angle 0 degree. Okay. So, that means, its magnitude is considered to be here and its phase angle is 0 degree, because we considered it is a reference phasor. Now, with this we will add all these two quantities, one is IR, another is JIX. Okay. Here J is our complex operator, J is our complex operator. In electrical engineering, we use this J to represent the complex operator. Okay. These things I hope everybody knows, this is the standard nomenclature we use being an electrical engineer. Now, how to get this phasor of this sending end voltage? Since if we write this equation again, this is basically V s is equal to V r plus I multiplied by R plus J I multiplied by X. Okay. So, this R and X represent the feeder actual resistance for this case, because it is a case with lumped load, and the feeder X represent the feeder's actual reactance. Okay. Now, that means, if we add these two drop with V r, then whatever quantity we will get, that will be the substation voltage, okay, or sending end or source side voltage. So, how to add these two drop? So, in order to add these two drop, first we have to locate the position of current phasor. We have to locate the position of current phasor with respect to the receiving end voltage, with respect to receiving end voltage, and here we put this current phasor I, considering that the load is lagging, considering that the load is of lagging load. Lagging load means they are of inductive load, they are of inductive load, which is true for the all practical loads, because practical loads are of inductive, which we know. Okay. So, that is why this current lags with respect to this load end voltage, that is V r, and we consider the standard nomenclature that this phasor is rotating anticlockwise. Okay. All these phasor quantities are rotating anticlockwise. So, we are taking at any particular instant a snapshot of this phasor, and which will give you a relationship with the sending end voltage and receiving end voltage, or source side voltage and load end voltage, or substation voltage and load end voltage. Okay. Now, since this I R drop, R is basically a scalar quantity. So, it should be in phase with this current. So, we draw a parallel this line to represent this I R drop. Okay. So, this I R will be in phase of this current I, and that is why they are in parallel. So, this I R basically phasor is basically a scaled value of I phasor. Okay. I is multiplied with some scalar R. Okay. Now, what will be this J I L x? So, this is not J L x. So, this is basically representing J I x, J I x. Okay. Now, this J I x means we have a J operator over here, and J operator we know it has a unity magnitude, but 90 degree phase shift. So, that means this J I x phasor will be in perpendicular with respect to this current phasor. So, let us draw a perpendicular with respect to this I phasor. So, whatever we will get, that will represent this J I x. Okay. So, this J I x again will be a scaled value of this I phasor, but it should be in perpendicular with respect to I. Now, here this phasor diagram is drawn considering that x is higher than r, which may not be true, for a distribution network, because in distribution network normally r is higher than x, but this figure is an indicative only. So, it does not represent the actual scenario. So, it is an indicative. So, in that case I r will be higher j with respect to I x. Okay. So, these magnitudes are would be different, but this phasor diagram will remain same. Now, we got these three phasor quantities, one is V r, that is this V r, one is this I r, that is this, and one is j I x, that is this. So, these three if you add, then whatever you will get, that will represent the V s, that is substation voltage or source voltage. Okay. So, this gives us the phasor relationship, and this V s will be a certain angle with respect to this reference phasor, that is V r, and this angle is considered to be delta. Okay. And this is not theta I, this should be theta only. So, this I is lagging with respect to V r at an angle theta. I is lagging with respect to V r at an angle theta. So, this theta is, we call it a power factor angle. So, theta is power factor angle and it can be also named as phase angle of current I with respect to this receiving end side voltage or load voltage V r. Okay. So, it is basically the phase angle between the current phasor and the load end voltage. Okay. So, this since it is lagging, so we represent it I phasor is equal to magnitude I at an angle minus theta, and this V s is represented as V s this magnitude at an angle delta. This delta is the phase angle of this V s with respect to the reference phasor, that is V r. So, this delta is also representing the phase difference of V r and V s. Okay. All right. Now, what we will do? We know that this percentage voltage regulation for this line is this, and we also know that if we apply this equations, that V s is equal to, if we replace this V s phasor with V s at an angle delta, V r phasor with V r at an angle 0, this I phasor with I at an angle minus theta, and this j I x phasor with j I at an angle minus theta multiplied by x, then we will get these equations. We will get this equation. Okay, where this is nothing but this V s phasor, which is equal to V s at an angle delta. So, if you convert this from polar to Cartesian, then you will get V s cos delta plus j V s sin delta. Similarly, we know this I it is basically equal to this I at an angle minus theta. So, if you convert again from polar to Cartesian, it will be I cos theta minus j I sin theta. Similarly, r plus j x is known to us. Now, with equating this real side with this real quantity of the left hand side and real quantity of the right hand side, we get a relationship of V s cos delta is equal to V s cos delta. So, I can write it over here. So, we get it V s cos delta is equal to V r plus I r cos theta plus I x sin theta. Okay. So, here this j and this j will be multiplied. So, this will be minus j square. So, which will give you 1. Okay. So, this will be I x sin theta. So, this will be the equations by equating real part of both the left hand side and right hand side equation. Now, once you get that, we have some approximation that V s cos delta is equal to V s. Why it is so? Because this delta angle is normally close to 0, this delta angle is normally close to 0. Now, why this delta angle is close to 0? Because if you look at this phasor diagram, generally these phasors, this V r and V s, these phasors magnitude wise they are much higher than these two drops, that is I r and J I x. Okay. So, voltage drop is some few percentage of the actual voltage, maybe 5% or maybe maximum 9 to 10%, okay, that much only, but it will be some fractional part of this actual voltage quantity. So, therefore, if it is so, then this angle, if you draw this in scale, then it will be something like that. If suppose V r is that much, then these two drop will be that much only, which gives this V s like this, and which is eventually make this delta angle very close to 0. Okay. So, which is true for any sort of practical distribution feeder. Now, once it is written that V s is equal to approximately V s cos delta, it is replaced in the left hand side. So, we get this equation. Okay. And you know this V s minus V r, this V s minus V r, these are the magnitudes only, the difference of the voltage magnitudes at the substation voltage and at the load end voltage. This is nothing but the voltage drop, which we are intending to derive. So, this will be equal to I r cos theta plus I x sin theta. Okay. So, that means our voltage drop becomes I r cos theta plus I x sin theta. Okay. Now, if you want to convert this voltage drop, if you want to normalize this voltage drop, then what you need to do? You have to divide it with some base voltage. Now, here we are dividing this with this base voltage, where V base is the base voltage to normalize the voltage drop, Now, once we divide this both side of the equation, so left hand side we will get voltage drop per unit, that means whatever value of voltage drop will come, that will vary between 0 to 1, and right hand side this equation will be I r cos theta plus I x sin theta divided by V base. Okay. Now, we have some further simplification of that equation. We know that complex power at receiving end holds these equations. So, we also know this from this equation P r will be equal to V r I cos theta and Q r will be equal to V r I sin theta. Okay, because you know that V r its angle is 0 and I conjugate its angle becomes I at an angle theta. So, this if you determine, then you will get this equation. Now, in this equation we got this I r cos theta plus I x sin theta. So, if you multiply both numerator and denominator with V r, then in the numerator we will get V r I cos theta multiplied by r plus V r I sin theta multiplied by x divided by V r V base, which is nothing but this V r I cos theta, as I said, it is nothing but P r, that is P r multiplied by r, and this is nothing but Q r. So, this is Q r multiplied by x divided by V r V base. So, this is exactly what is done over here. Okay. And then you arrived at these equations. Okay. This equation, and further simplification is possible if you put this P r is equal to S r cos theta and Q r is equal to S r sin theta, where S r is basically the complex power in kVA or MVA. So, in distribution network normally load demands are in kVA. So, if you put this, you know that this relationship of active power and reactive power with this complex power, that is active power is equal to this complex power multiplied by cos theta, reactive power is equal to complex power multiplied by sin theta. So, if you replace this P r and Q r with this, we will get this relationship. Okay. So, this gives you this relationship of V du as a function of S r, that is the complex power or kVA demand of the load. Now, finally, we arrived at this expression of voltage drop in per unit, that is equal to, we can replace R is equal to small r multiplied by L effective, okay, and we also replace x by small x multiplied by L effective, where small r and small x they are resistance and reactance of line per unit length, and if you multiply with this effective length of the resistance. So, then you will get the value of R, and similarly you will get the value of capital X. So, if you replace this with this, this here L E is basically representing this effective length, okay, effective length of the feeder. So, you will get this one, and this S r is basically representing 1/3 of S 3 phase, where S 3 phase is basically 3 phase power demand of the load, because loads for a primary distribution feeder are of 3 phase. So, its demand is represented by 3 phase demand. So, 1/3 of that will be S r. Okay. So, we get this relationship. This is what our V d per unit means its value will be a fractional lesser than 1, and if you multiply it with a 100, then it will be percentage voltage drop. So, percentage voltage drop, percentage V d is equal to V d per unit multiplied by 100. Okay. All right. So, we get the relationship of voltage drop as a function of this feeder parameters, feeder line parameters, and also as a function of this feeder loading and this effective length. Now, we know this actual voltage drop equations, it varies, as already we have mentioned, this voltage drop is proportional to L effective multiplied by S, okay, where S is basically the loading load demand, okay, and its proportionality factor is nothing but the parameter k. So, L e into S. Now, if you compare these equations with previous equation, then this is effective length of the feeder and this is what my loading. So, if you exclude this, whatever will remain, that will represent the constant of the proportionality, that is parameter k, that is constant k. So, constant k equations is coming out to be this. Okay. And now, you can understand how this constant k is, what are the parameters which basically impact on this value of this constant k. Now, you can find that this is a function of r. So, basically constant k is function of r, it is also function of x, it is also function of theta, it is also function of voltage, okay, V r and V base. That means, this constant k, this parameter k, it is represented in capital K, it depends upon this line resistance and line reactance. That means, it depends upon the line impedance, also it depends upon the power factor of the load, also it depends upon the voltages. Okay. So, these are the things which will influence the value of this parameter k. Okay. So, for a typical feeder, we can simply replace this effective length and this S 3 phase by this, and you can find out the expression of voltage drop like this. Okay. So, this can be understood. Now, we have some interpretation of voltage drop formula, and we will try to understand what are the parameters directly influence this voltage drop of a typical feeder. What are the parameters which influence this voltage drop expression? So, we have 4 different cases. This is case 1, this is case 2, this is case 3, this is case 4. So, in first case, we assume that all other parameters remain same except the length of the feeder is double, this multiplied by 2, this symbol is shown multiplication. Okay. So, keeping all other parameters same, what would happen if the length of the feeder becomes double, or if we increase the length of the feeder twice of the actual length. Then looking at this equation, you can understand this, if this feeder length is double, then voltage drop, because first of all this area of this one feeder will be 4, because 4 times of the actual feeder area, because already we know that A is equal to L square, this already we determine. In fact, this is true for both this is proportional to L square for both the square service area, square and hexagonal service area, hexagonal service area. Okay. So, that means, if we make this feeder length twice of the actual length, the area that the feeder can serve will be 4 times of the actual feeder area, or feeder service area will be the 4 times of the actual feeder area, and this will also increase this kVA or load that the feeder can serve, and this will increase the voltage drop 8 times of the actual voltage drop, because already you know this voltage drop V d, it is proportional to effective length cube. Okay. If length of the feeder increased twice, so voltage drop will be increased 8 times of the actual voltage drop. So, which is of course, not permissible. So, that is why length of the feeder, if we increase, it will have direct impact on this voltage drop. Second case is, if load density is increased twice, keeping all other parameters same, load density of the feeder is increased twice of the actual load density. So, that means capital D is increased twice. So, actual load density will be 2 multiplied by this usual load density. So, what will be that impact? This will impact, because this area of the feeder will remain constant, because area of the feeder only depends upon the length of the feeder, but this load served by this feeder will be twice of this actual load the feeder is serving, because you can remember S n is basically equal to capital D multiplied by A n. So, if you increase capital D twice, then S n will be increased by 2 times, and since S n will increase, voltage drop will also be increased twice, because that voltage drop is directly proportional to the loading of the feeder. Okay. So, that means, if load density increased to twice of the actual value, it will result in twice of the actual voltage drop. Okay. Now, the third case is, if we add new feeder, that means, keeping all other parameters same, number of feeders we increase to twice, that means, n is increased to twice n. Okay. So, what will be that impact if we have same amount of customers, but we increase the number of feeder? Of course, this area served by one feeder will be half of the actual feeder, and which will result in actual voltage drop would be which will result in the voltage drop will be half of the actual voltage drop. Okay. Because if area becomes half, and then obviously this load demand will be also half, load which is served by one feeder will be also half, and which will result in voltage drop becomes half of the actual value. Now, sometimes we change the conductor. So, this is called feeder reconductoring. It is also called conductor replacement, conductor replacement. Okay. Suppose if we have a feeder and its conductor size or its conductor we change. Okay. And what will be the impact of this? Since you know the constant k, in that case your number of feeders will remain same, the feeder service area will remain same, everything will be same, but this constant k which depends upon, which proportional to this feeder parameters r and x, this will change. Okay. So, if we assume that this k becomes half, then this will also directly impact to the voltage drop, because voltage drop is proportional to the parameter k as well. So, if k becomes half, voltage drop will be also half. So, these are the 3 possible cases, sorry 4 possible cases which we can study. So, if you look at this my interpretation on this, which is written over here. So, case 1 is if the length of the primary feeder is double. So, which will increase the voltage drop 8 times, okay, which results in the voltage drop 8 times, and therefore, increase of feeder length should be avoided. Okay. This is one of the thumb rule. Then case 2 is if the load density is double, then it will result in voltage drop of the feeder to be double. So, therefore, increasing load density negatively affects the voltage drop. So, these are the interpretation. Now, if the number of the feeders is double, so what we will get, the voltage drop would be half, each of the feeder voltage drop, main feeder voltage drop will be half. Therefore, new feeder addition is helpful to reduce the voltage drop. If you get a voltage drop, a typical feeder is very high, we can exercise this option. Of course, it needs some capital investment. Okay. Now, if the conductor size is double, which reduces the value of k by half, and thereby it results in the reduction of the voltage drop to the half. Okay. So, these are the possible cases. Now, we will discuss 2 numerical examples related to this. Look at this first numerical example. So, in that numerical example, we have a substation located at this point. So, here is the substation, and this is the main feeder, this is the main feeder, okay. And these 2 are lateral feeders, these 2 are lateral feeder. Okay. Now, the dimension, the length of this main feeder is given 3300 feet, and this dimension of the laterals are also given 5760 feet and 5760 feet each. Okay. Now, it is mentioned that all are of 3 phases. So, all this is the single line diagram. So, all feeder, this feeder is of 3 phase, and it is also mentioned that how much load demand each of, how much load is carrying by the main feeder and the lateral. So, this main laterals are carrying 518 kVA each, and main feeder is carrying 1036 kVA. Okay. So, it is also mentioned that what is the value of K constant. So, K constant for laterals are given to be 0.025 percentage voltage drop per kVA mile, okay. And the for main feeder K value is given as 0.01 percentage voltage drop per kVA mile. And it is also mentioned that for lateral feeders load is uniformly distributed, and if nothing is mentioned, it should have been also mentioned that they are of rectangular service area, So, if nothing is mentioned, we assume that it is automatically rectangular service area with uniformly distributed load. And for main feeder it is lumped at the end, that means for main feeder the load demand is lumped at this point. So, we have lumped load, okay, lumped load. Okay. So, these informations are given and you are supposed to determine the percentage voltage drop at the ends of the lateral and at the main, that means percentage voltage drop at the ends of these two end A and A dash, and at this point let us consider this point is let us say B. So, percentage voltage drop at this point as well as at these 2 points A and A dash. Since both the laterals are identical, so you can assume there will be same voltage drop at the end of both the laterals. Okay. So, in order to find out voltage drop of the laterals, since they are uniformly distributed and we assume that service area of the feeder is rectangular. So, the voltage drop expression will be effective length of the feeder, that is L by 2 multiplied by this constant of the proportionality, that is K, multiplied by S. Okay. So, this is nothing but the expression for voltage drop and we know the values of all. So, this one is basically converting this mile this feet to mile, because ultimately this expression for capital K or parameter K, it is its unit is percentage voltage drop per kVA mile. That means, we have to multiply it with the kVA demand that it is feeding and with the effective length of the feeder. So, if you can multiply, then you will get this voltage drop. So, effective length for this type of feeder is half of the actual length and S is already given, that is it is 518 kVA. Okay. And K value we directly took it from here. So, K value of the lateral feeder is 0.025, if you put it over here, and this is K value, this is value of S, this is the value of L effective. So, once you multiply all these things, you will get this percentage of voltage drop directly, because K parameter is given to be percentage voltage, not per unit voltage drop. Okay. So, this is coming out to be around 7% voltage drop. Okay. Now, 7% voltage drop will occur between this point B to A dash and between these 2 points B to A. Okay. This one has to understand. Now, for determination of voltage drop at the main feeder, which is having lumped load. For lumped load, we know that effective length is equal to actual length. So, in that case you simply this is representing actual length of the feeder in mile. So, this is L in mile, this is the value of K and this is the value of the load it is serving, that is S. So, if you multiply these 3, we will get the voltage drop at this point B, at this point B, at this point B. So, that means from substation to B, we get a voltage drop of 6.475%, and from main feeder to the laterals from B to A dash, the voltage drop we got as 7.06%. Okay. So, total voltage drop from this in the primary feeder, starting from the main feeder to the lateral, will be simply summation of these two, arithmetic summation, which is equal to 13.535%. Okay. So, this is what the answer. All right. Now, we have another example, another numerical example. Okay. In this example, it is mentioned that we have a square shape, service area under a distribution substation, which is located at the center point of the service area. So, this is where your distribution substation located. Okay. This is where the distribution substation is located. This is what your main feeder starting from A to B, and these are the laterals, which is known to us. So, here it is mentioned that the voltage these feeders are of 3 phase 4 wire, okay, and the voltage line to line voltage of the feeder is given 4.16 kV. the power factor of the load is given 0.8 and the load density is given as 1000 kVA per kilometer square. Load density is given as 1000 kVA per kilometer square and it is uniformly distributed load density. But because of this the service area of the feeder is square and we have 4 number of feeders like this. So, service area under a particular feeder will be of course triangular. So, this is what the service area under a feeder, Okay. Now, the ampacity limits are given as 230 ampere and this capital K, that is parameter K value is given as this 0.05% voltage drop per kVA mile per kVA kilometer. So, we are supposed to determine the maximum load for the feeder, assuming that this feeder is thermally loaded, that is feeder is of TL. Okay. Also the substation size and percentage voltage drop. Similarly, assuming the second question is question B is this was question A. Okay. Question B is considering the feeders are of VDL feeders, that means feeder is a voltage drop limited feeders, where this voltage drop is limited to 3%, voltage drop is given to be 3%. You are supposed to determine all these 3, one is maximum load per feeder, substation size and ampere loading of the main. Okay. So, previously it was voltage drop, but here voltage drop is given to be limited at 3%. So, we are supposed to determine the loading under this particular condition. Now, look at the solution. Now, first of all, since in this case A, in this case A, the feeders are of TL feeder, that means thermally limited feeder. So, here feeder loading is limited by the ampacity limit of the conductor. So, we know this ampacity is given as 230 ampere. We also know that the voltage of the feeder is 4.16 kV line to line. So, we can determine that maximum possible loading per feeder is nothing but root 3 multiplied by V L multiplied by I. So, this gives you root 3 multiplied by 4.16 multiplied by 230, this gives you that much of kVA, okay, 1657.2 kVA. Now, since we have 4 identical feeders for typically this type of substation service area. So, total substation size would be 4 multiplied by the maximum loading of each feeder, that will be equal to 1657.2, that is given to be 6628.8 kVA. Okay. Now, in order to get voltage drop, we have this is solution number 1, this is solution number 2, and in order to get a solution of the third question, that is total percentage voltage drop, let us first put this voltage drop expression. This is nothing but effective length of the feeder, this is parameter K, and this is nothing but that load the one particular feeder is serving. So, this is effective length of the feeder. This is also of course, that is constant K or parameter K, and this is the load which is serving by a particular feeder, So, K is known to us, only thing you have to know that length of the feeder, which is not given here, but we can find out once you know that how much loading you can do in a particular feeder. So, which is given over here. So, we know that S n is equal to D multiplied by A n, which is equal to D multiplied by L 4 square for a this type of feeder. From this D is known to us, S n is known to us, we can find out L 4 like this, which is coming out to be 1.287 kilometer. Now, once you get this L4 or length of the feeder, you put it this expression, you get this value of the percentage voltage drop, which is coming out to be 7.1%. Okay. This is for case A. Now, in case B, we know example for VDL feeder, voltage drop limited feeder, where the voltage drop of the feeder is limited to a given percentage of voltage drop. Now, for VDL feeder, you know, it is percentage voltage drop is given. So, we put this is the expression of voltage drop. So, here K is known to us, D is also known to us. So, therefore, we can find out this only unknown quantity is the length of the feeder. So, L4 is the unknown quantity, So, therefore, we can find out the value of L4 from these known quantities, and it is coming out to be 0.965 kilometer. Okay. So, this will give you that maximum load per feeder, which is D multiplied by this area of this area served by particular feeder, which is L4 square. So, that is coming out to be 931.2 kVA. So, this is the solution 1. Once you get this solution, solution 2 is very easy, since we have 4 identical feeders. So, the total load that the substation can serve, which is equal to 3724.9 kVA. And this is the solution of third questions, that is the ampere loading of the feeder or the maximum loading of the feeder. If you want to limit this voltage drop to be 3%, this is equal to S divided by root 3 VL. So, line voltage is given, S n is known to us, that is this 931, and so if we put all these things, we will get 129.24 ampere. Now, at this point, let us compare these two solutions to understand what is the difference. So, here you can see when your thermal loading is limited, then length of the feeder is much higher than this feeder, okay, and that will result in higher amount of load it can serve, okay, and also that will result in higher amount of voltage drop. But when we limit this voltage drop to 3%, which is means less than half of this actual voltage drop, then length of the feeder becomes less, but you can serve lower amount of load under this condition. Under this condition, substation size also becomes very less as compared to the previous example, which was 6600. Now, here it becomes 3700, almost slightly higher than half of this value, but here this ampere loading is also less. It means that it is this load that it is serving is much lower than the ampacity limit, or the maximum serving load is limited to very less value as compared to what it could have been served by this ampacity limit. So, this is what one should understand. Now, another important thing is that, because with this I will complete this part of the lecture, which is distribution transformer, and this distribution transformer is the basically used to step down the voltage level, feeder voltage level to the utilization voltage level. In India, it is around 400 volt 3 phase, and which will automatically 220 volt single phase. Okay. And they act as a liaison between primary distribution network and secondary distribution network. Secondary distribution network basically we call the line beyond this distribution transformer, okay, which is directly connected to the customers, and they are this distribution transformer are of various ratings starting from few kVA to up to 500 kVA, and small distribution transformer which are rated less than 100 kVA, and so they are directly pole mounting in overhead distribution line, and larger than 10 kVA size they are installed in a platform supported by 2 poles. Underground distribution transformer are installed in street valves, in manholes direct buried or pad or ground level in the building. Okay. So, I am not going into detail of these different types of distribution transformer, because this is not purposefully kept in the syllabus of this course, but you can of course make a self study on different types of distribution transformers Only some few important things you should know, that heat is basically the limiting factor for the rating of the distribution transformer or capacity of the distribution transformer, and we have different type of coolant arrangement, cooling arrangement, which may be dry type of coolant and liquid filled type. Dry type of coolant is also called air cooled or air insulated distribution transformer, which are of very small size, nowadays rarely used. But liquid filled type distribution transformer are usually oil filled and is mostly used. Sometimes some extra blower is also fitted, which is called secondary coolant, in order to cool down this oil inside the transformer. And we have different types of the connection of distribution transformer, which I will not discuss in detail. Different connections of 3-phase, different connections of 3-phase distribution transformer. Which includes star stars, that means both primary and secondary side are connected with star connection or star delta, that is primary side is star connected, secondary side is delta connected. Similarly, delta star, which is primary side is delta connected and secondary side is star connected, or delta delta, where primary side is also delta connected, secondary side is also delta connected. But in distribution transformer, we normally use delta star connection for residential customers, because this star connection gives you flexibility to of having this neutral. Okay. And we need a neutral to supply the single phase loads, because residential customers mostly are of single phase load. So, this delta star is normally used, but different types of connections of distribution transformers are possible. They have individual merits and demerits. So, those things I will not be discussing here. If one has interest, he or she can have self study. Okay. All right. And also there are some other features like voltage regulation of the transformers, voltage regulation and efficiency calculation of the distribution transformer. Those issues are also usually taught in electrical machine course. So, I will not be discussing here. If one have any interest, he can have a detailed study on this, and in order to study all this concept, you follow this Turan Gunan's book, which is electric power distribution system engineering. Means third edition I have followed over here, but subsequent edition is also there. So, whatever materials I am providing over here in this course, mostly taken from this particular book, and if somebody wants to have a self study on this distribution transformer, he can go through this one chapter of this book, which is basically focused on the discussion of distribution transformer. Okay. So, with this I will complete this module 2. Okay. Thank you.